Hello guys. So today we will be starting from LP2 part 1, which is artificial intelligence, and in this we will be starting from group A question 1, which is to implement a depth first search algorithm and breadth first search algorithm, basically DFS and BFS, using an undirected graph and develop a recursive algorithm for searching all the vertices of a graph or tree data structure. So let's just see this. Already I have a video on DFS and BFS in C++ language. So if you want to check that out, you can go to the playlist section and there you can find out DSAL lab, which is data structures and algorithm lab, in which you will find the same. So let's just move forward and start. So basically DFS and BFS are two traversal algorithm or searching algorithm. So these are mainly used on graph and tree data structure. So graph is basically a collection of node and edges. So nodes are connected with edges and here. So let's say if we take a similar example, if we have an array, let's say of A, B, C, D, and E. So these are all the elements and we can traverse over this. We can search over this. How? We can start a for loop starting from 0, then 1, 2, 3, 4 up to the size of the array. And like this, we can traverse the whole array. But in the case of graphs, we need to use some other technique. So here, DFS and BFS helps us in traversing the whole graph. So starting with the DFS, what does DFS say? So as the name suggests, depth first search. So basically we have to go to the depth of any of the node, and if there is no other way, we have to backtrack and choose the other method. So assuming this graph will be, let's say, starting with this node. So after starting with this node, what would I do is I would go to any of its child. So I came here, I will traverse this, then any of the other node, I will go to this, I will traverse this, I will try to go to its child, but there is no child. So what would happen? I will revert back. So here I will try to search the other child of this node. So here I got another child, then again into the depth, again I found nothing. So I will go back. I will try to check other child of this node. So basically here you can see we are coming back to this because it is also a child. So assuming, let me just change the color. If I assume this is the node, uh, this is one of the child, this is one of the child, and this is one of the child. But already we came from this node. So basically this is the parent. Or in the tree we can say as parent. Or here we can say these are also the child nodes. So it will try to visit these two. So what we have to do is we have to keep some kind of array which says that which all nodes we have already visited. As we can say, this is already green means it is already visited. So we can say that this node, let's say this is A, B, C, D, and E. We can say A was already visited, B was already visited, D is also visited, then C, then E. So basically all of them are visited. We are selecting a node. So select a node, then go to its child until and unless we don't get until no childs are there. So when no child, return back and go to other child. So another child. So another child. So basically we have to do until and unless all the child are not marked. All the child are not marked. Okay. So we have to basically do this thing for the DFS. Similarly, if we again take an graph, so let's say this something like this. Okay. If we consider some kind of this graph, what we have to do is again we will be seeing the BFS breadth first search. So basically it is level wise traversal, or we basically go in a level wise order. We will see how it works. So starting with a select start node. So let's assume this is my start node. What I will do is basically I will go to the child of this node. Instead of that, what we can say is first I will be starting with this node, then I will be traversing this, then this. So these are childs of this node. Then what we will do is we will traverse the childs of this node. So instead of telling this and that, let's just take A, B, C, D, and E. So let's say our starting node is A. I will visit all the child, I will mark all the child of this A. So it will be B and it will be C. Then what I will do is I will take out B and mark all of its child. So it will be C and it will be E. Similarly, sorry, D and E. Then what I will do is I will go to the child of every child of C and mark them. So C has only one child, E. Then I will go to the D and mark all of its child, which is E, which is already marked. So we don't need to mark again. Then I will go to E and I will mark all of its child. So it is basically B, D, and C. So we don't have to do that because they are already marked. So here also the same concept comes as visited array. Why? Because if I go to E and say B, D, and C are my child, then again I need to start from B and mark all of its child. So what would happen is it would get confined into an infinite loop, which would then not break, and the BFS traversal would become an endless traversal. So we need to take and visited array where we see A is marked whenever we visit A. Then we could say B is marked, then C is marked, then D, then E. So like this, whenever all of them are marked, we can say the whole graph traversal is complete. As currently we don't have any fixed point or goal node. So as we are studying in AI, so here this DFS and BFS is called uninformed search. Why? Because we don't have a clear idea from where to start and up till where we have to go. So we don't have a start or a goal node, initial and a goal node. So we don't have these. So therefore it is called as uninformed search. And yeah, so let's just see how we can implement this in programming way. So assuming uh, let's say we have to represent a graph like this. Let me take okay, graph A, this is B, this is C, this is D, this is E, this is connected to this, V is connected to D. Let's take this graph. So here we would have to generate a representation of this into the programming format. So you may have known about various techniques, adjacency list, so adjacency list or adjacency matrix, and few other things. So let me just give a brief on this. So adjacency list is basically a list of all the nodes. Let's say A, B, C, D, E, and A will have a list of all the members it is connected. So A is connected to E and B. B is connected to let's say A, C, and D, and similar. So this was a wrong representation. We basically store something like into the hash maps or map. In Python, we use dictionaries. So it would be like, let's say graph G, and A is equal to list of E and B. Then not equal, this should be colon. So yeah, so colon, then B is equal to A, C, and D, and something similar to all of this. And if it is empty, we can just give an empty array. So this is how we can represent graph in adjacency list format. As you can see, adjacency list means adjacent list of elements which are as adjacent to that node. So currently, if A is a node, this is a list of adjacent nodes. So again, coming back to this graph, then we would have the adjacency matrix. So here what we have to do is we have to create an 2 by 2 matrix of number with having rows and columns equal to the number of nodes in the graph. So let's say here we have 1, 2, 3, 4, 5, 5 nodes. So we will have 5 by 5 matrix. So here 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Let me just scale it a bit. Just okay. Hope so this is visible. And yeah, let's just start. So here instead of 1, 2, 3, 4, we have to use A, B, C, D, E because nodes have the name A, B, C, D, and E. So what we are doing is at this position, we would say if A is connected to A or A has a node, A has a node to A, then we would write 1, or in the case of weighted graph, we would write here the weight of that element. But currently, as we have undirected, we will write 1 or 0. And yeah, so A to A, we have nothing. A to B, we have one node. A to C, we have nothing. A to D, we have nothing. A to E, we have 1. Similarly, B to A, we have 1. B to B, nothing. B to C, yes. B to D, yes. B to E, no. C2, and similarly we will continue the whole thing. So this is how the adjacency matrix looks like. So here we have basically mentioned 0 when there is no edge between those two nodes, and 1 when there is an edge between these two nodes. So this is how we store the graph in adjacency matrix form. But as you can see, there are redundant 0 which we don't require. So for the space optimization, adjacency list is better. So with the same idea as adjacency list is better, we will choose adjacency list and create a program for our BFS and DFS. So let me just copy this graph so that we could now see how to implement BFS and DFS. So here is our graph. Now let's just start with DFS. So in the DFS, we would need a start node. Let's say the graph first and then the start. Okay. So what we are doing is if we are at A, what we are doing is we are going to each element of each children of that A. So what we can do is if I assume G as to be an adjacency list, G of A would give me a list of E, B. Why? Because this is adjacency list. So G of A gives me this. So what I can do is if G of A gives me a list, I can traverse over that. So what I will do is, or simply uh, for I, or let's say for C, which is child, in G of S, yeah, start node. So for G in S, where S is A, so it is the starting node. So here G is A and S is A, which is the starting node. So what we'll do is for each C in G of S, what we will do is we will again perform the same steps. So let's say I select this and remove from the graph. And now I can say that E is an starting point and I have to again perform the same DFS thing. So this A doesn't matter so much while if we ignore that. So basically what we are doing, we are performing the same thing again, which we can call it as recursion. So recursion is function calling function or doing the same task again and again. So here we will be doing the same thing. So what we will do is we will call DFS of the same graph, but the node is changed, which is C. So I will do like this. What will happen? It will go to E, then E's child is C, then C's child, let's say D, and then again D's child B. Then I will come back, and D would go to the other child, which is C also. So if I take some other example, let's say I started with A, I move to E, then I move to C, And as C is also child, C has child E, B and D. So let's say C again comes back to E, then E would again go back to C, then again C would come back to E. So this would create an infinite loop. So what we have to do is we have to, as I mentioned, we have to create a visited array. So we will create a visited array which would have all the elements, and let's say we will initialize each of them with 0. That's saying that it is not visited yet. So what will I do? Whenever I have to call a DFS, I'll first check whether already it is visited or not. If not visited, and let's say the child, if child is not visited, then only perform the DFS. Okay. So now we can see what will happen is, instead of this list, as we are using uh, adjacency list, we would also need to create a list for this visited too. So visited would be, and sorry, a dictionary, A equal to 0, B equal to 0, and so on. Okay, for each of the node. So this then would be the function. So this would basically be how it would be. But if we again check out, we have we are checking that it is not visited. So we are checking here the node is not visited. But we have never mentioned when is the node visited. So let's say here we have colored A because why? It is visited, E which is visited, C which is visited. But we never say in our program that these three nodes are visited. So what we have to do whenever we come inside the DFS function. So as you can see in the graph also, when we come on A, we directly mark it. When we go on E, we directly mark it. So whenever we come inside the DFS function, what we have to do is we have to use the node. So visited of that node, let's say S, because it is a start node, equal to 1. So 1 basically means true, or you can also use true. But for time being, I will use 1. And this is the whole code of the DFS. So basically, DFS would need an visited array. It would have all the elements. We will be starting with defining a function. Let me just change the colors. So yeah, we will be declaring a visited array. Then we will be starting with a function initialization of DFS. It would take a graph and then start node from where to start. So whenever we come inside this function, we will be assigning that start node as visited, as we have visited that. Then for each of the child, in of S. So let's say this is start node. So for each child of start node, what we will do is, if it is not visited, then we will call DFS again. If it is not visited, we will call the DFS again. So basically A will be there. It is visited. Okay, blue color visited. Then it will go to each of the child. So first it will go to E, then it will go to B. But as we are first going to E, we will then go to let's say C. So if we go to C, then it would again go to its child, which is E. Let's say it goes to E. But while checking here, if not visited of C, means if child is not visited, but E is already visited. So we will move to the next child, which is D. Then again D will check, and let's say if again finds that it is coming back to C, but it is already visited, so it will go to the next child, which is B. So it will come here, mark here, then it will try to go to its child, which can be A, which can be D, but both are visited. Then it will backtrack, it will come to D, all of the childs of D are marked, then it will come to C, uh, then it will check for the other. E was already done, D is already done, so it will go to B. So it will try to B, but it is already visited, so it will come back to E. E will go to the next child, which is A, but A is already visited. Then E will backtrack to A, and after that A will be trying to go to B because it is the second child, but it is already marked. So like this, the DFS will work. So let's just quickly program this. So let's just start with the programming. So here, let's just take an direct input of graph. So I will have a graph. So let's say 0 is connected to 1 and 2. Okay. Okay, let's just uh, create a graph first, or we can consider this graph, or we will consider this graph itself 0, 1, 2, 3, 4. So 0 is connected to 1 and 2, 1 is connected to 0, 3 and 4, 0, 3, 4. 2 is connected to 0 and 3. Okay, 3 is connected to 2, 1, 2 and 4. 4 is connected to 3 and 1. Okay, so we will create 0, 1, 2. So this should be the graph. Let's quickly define the function DFS. It would take a graph and a starting node. Here we will mark visited of S and the starting node as 1. Then for child, say in G of S. So for all child of G of S, if not visited of child, if child is not visited, then we will again call the DFS. If it is not visited, we are calling it again. On the graph same, but child different. So here we would need an visited array. So visited, okay, not an array, visited dictionary, which should have 0. Or we can also take here list, because list or array, because here we are starting with 0, 1, 2, 3, 4. And basically we need 4 element. So we can 0 into 5, sorry, not 4, 5. So I will use a list comprehension here. So this would create a list comprehension. And if you are not sure, let's just print. So let's build this. So here we can see, okay, it came and double headed. Yeah, so 5 elements. So we have visited now. What we will do is we will execute DFS. We will pass the graph and the start node as 0. So this should complete, but it won't print because we haven't printed. So whenever we visit, we will print the node S. So let's execute, and here we can see 0, 1, 2, 3, 4. All of them got printed. Let me just change few arrangement. Same nodes, but the arrangement to get in different traversal. Okay. Yeah. Now 1, 0, 1, 3, 2, 4. So basically our DFS is working fine. And here we have successfully created a program for DFS. So now let's move forward to the BFS algorithm. It will also be a similar algorithm, but with a few difference. So let us see how it works. So as we just said that BFS works level wise. So first it will go to the A, then E and B together, then the child of this. So for the child of this would be C, and then the child of B would be C and D. So like this, it will go this level, then these are two in the same level. How? A is connected to E and B, B is connected to B is connected to D, and E is connected to C, something like this. So we have some structure like this, and C is connected to D. So what will happen is first A will traverse E and B, then C and D. So like this, it works on level wise traversal. So yeah, let's just head on and see how we can do that. So starting out, if we just say we will start with A, then we will go to its child E and B. Then we will choose the first element, and then we will go to the child of that, which would be C. Then for B, we will go to the child C and D. C is already visited, so we'll go to D. Then for C, what we will do is we will go to its child. So these are B, E, and D, but those are already visited. Then we will go to the D's child, which is C and B, which is already visited. So basically, this is how we visit. So if you could say, first the A comes, A goes. Then E comes, E and B comes. Then E goes, C comes. Then again B goes, C and D comes. C is already there, so just D comes. Then again C goes, then D goes. So basically here you can see some kind of a fashion which is first in, first out. So here the elements are coming at the first and going at the first in, first out. So this is given by a data structure which is queue. So here we will basically using the queue data structure to do or perform this kind of operation. So let me just remove and yep. So let's just start. So here I would be considering this queue. I will be starting with node A. I will put node A. I will remove this. Then I will go to its child, which is E and B. So E and B will be appended into this. Then what I will do is I will go to the E, remove E, and go to all of its cells. So here basically A and C. So A is already visited. So we will put C here. Then we will go to B. We will remove B and go to its cell. So basically A, C, and D. A, C are already present. So we'll put D. Then we will remove C. C will try to add all of its cell, but those are already added. So we go to D. D also already added. So what we see here is if we try to programmatically write, what would be is let's define a DFS, BFS. We would require a graph and a starting point similar to DFS. But here, what we will do is we would need a queue. Queue equal to, let's say I will take an empty list because here we can perform the same actions as of queue in the list also. So list dot push, sorry, list dot append will add at last and dot pop 0. So I can mention an index to remove that. So pop 0 will be removing the first element. What I will do now is I would also need an visited array. So I will take an visited array and I will put start into this. And I will also put start into the queue also because it would be the starting element. Or else what we can do is we can use the queue itself as no, we would need a separate thing because we are removing. So we will add visited as start. Now you would have a question that why we are using visited here inside the function, and in the DFS case we used it outside the function. So if we go back to the DFS case, here what we are doing is we are performing recursion. So here you can see DFS, we are performing recursion. So for recursion, the data which are we store into the function doesn't persist, or it is frequently changing for the each function call. But we need this visited array to be permanent and consistent for all the functions. So we decided this outside the outside the function. And here what we are doing is we will be implementing this without recursion and using the normal iterative thing. So here we will be, so that's for why we are using this visited inside the function. And you would ask, how would you know you are using recursion or you are not using recursion? It depends on the thing, how you are implementing. Here the recursion code was simple, so I used this. Here you can also implement and similar code with the stack also. So here you can see, first I go to the A, then E and B. But what I do is I then, okay, here I would need to write in a bit different order. So I start with A, I go to B and E, let's say. Why? Because E will be removed and we will go deeper into E, let's say C. Then we will go deeper into C, which is D, and then traverse back to C, traverse back to E, traverse back to B, traverse back to A, and something like that. So here we can use a stack and we can use last in first out. But here, as we need first in first out, we will use queue. So we will be starting with this queue and visited. Then what we will do is while queue is not empty, or we can directly write while queue. So what we will be doing is for each element in queue, so we will remove the first element. So let's say int, okay, sorry, Python is dynamically typed. So current equal to q dot pop. So removing the first element. Then what I will do is for all the children's in this current. So for C in graph of current, something similar to what we did in DFS. So we are going to all the elements of graph, and what we are doing, if not visited, so if C is not visited, then we are adding it to our queue. So queue dot append C, and what we are doing is visited dot append C, because it is now visited. So if not in here, as we are not using index, what we can do is we can use for not in vis, because here we are appending the element. So for not in vis we can use, so it will traverse over the visited array, and if it is not present then it will be true, and we can append. So let me just string a bit. Yeah, so this is the whole BFS code for the graph. So this is the BFS code. So here what we are doing, if I quickly go through this, here we are defining a BFS function, taking graph and starting node, adding starting node to queue, adding starting node to visited because it is already visited, then means we are starting with the program, then we are visiting. Then while queue is empty, so until and unless the queue is empty, because what we can see is we are removing each of the element. So while until and unless queue is not empty, so once it becomes empty, it will give false and it will go out of this while loop. But now if queue has some elements, we will pop the first element, put it in current, then we will loop through all of the childs in current. So what will this do is we will go to E and V. So here we can go to E and V. So we will go to those nodes, and then if it is not visited, if it is already not visited, then we will append to queue and append to vis, and the loop will continue. It will check for queue and other thing, and this would work. So let's get back to the coding thing, and let me just comment out this and this. So yeah, I will consider the same graph. Let's just start with define BFS. Would need a graph and starting point. Then Q equal to empty list with S, and yeah, visited equal to also S. Okay. So here then while Q, so until and unless Q is valid or it has some element, current equal to Q dot pop 0. Once we remove that, we will go to all of itself or C in queue of current for every child. What we will do is if not in vis, we will append. So q dot append. So q dot append C, adding that child, and vis dot also append C. So where we would print. So whenever we are popping, let's just print it that time only. So print, and let's just call the BFS and see. Graph and start node would be 0. So if not in vis, okay, if C, what is not in vis? So if C is not in vis, means the child is not in vis, then we would do this. So still we have some issues. So current equal to pop 0. List index out of range. Okay. Uh, here, okay, it is not Q, it is G graph. And executing this, we will be getting the whole traversal. So this is how we would use the BFS and DFS traversal in Python to traverse the whole graph. So this is all for this video. Let's just meet in a new video. If you have any doubts, please comment in the comment section below or join the community and you can ask the questions there too.